This video is for Math 0242-1342. As we start Chapter 3, we're going to be doing Section 3.1 and 3.2, which is as far as the first test goes. So this is the fourth video so far. We had the introductory video that included Sections 1.1 and 1.2. That was one video. Then the second video covered Section 1.3, 1.4, and 2.1. There was a third video covering 2.2, 2.3, and 2.4, and now this fourth one's doing 3.1 and 3.2. And there'll be a fifth video for this unit that will cover the review. And then you got to complete all the homework and the review by the time the test is due. The test might not be visible to you right now, but maybe it is. But it may not be visible until it opens on October 6th at midnight. And then you get a 48-hour window till the next day at the end of the day, 11:59 p.m. on October 7th. And you do need to use the lockdown browser and webcam to take the test. So all the homework and review are due on October 7th at 11:59 p.m. because that's when you're taking your test. And again, there's no videos for the 0242 homework. It's just extra resources for you and extra chances to master what you've learned and or do some easier problems that are maybe giving you some knowledge that the people that only take 1342 are just supposed to know already. So work those on your own. If you have any issues with them, definitely either email me or go to the tutoring if it's a case of you don't even know how to do it. But a lot of the problems in there are easier versions of stuff we're doing already in the 1342 class. Okay, so 3.1, 3.2 has 15 questions. Select the appropriate word or phrase to complete each sentence. The blank is resistant because it is not affected much by extreme values. Okay, so the section 3.1 is called Central Tendency. We're going to try to measure where's the center or the average of a data set. Central tendency. There's three very common ways to measure average, and then there's a fourth one that some people probably haven't heard of before. But the first three are taught as low as junior high, and then you see them again in high school and now in college. The most common way to measure the center or the average is called the mean. The mean is when you sum all the numbers up and divide by how many there are. Sum divided by total. Most things that involve averages use that, like in school we have our test average or our overall average. In sports they'll do like a batting average or a rushing average. So averages are used a lot, even like with salaries. What's the average salary of a teacher, average salary of a lawyer, things like that. They just add them up and divide by how many there are. The second one is called median. This is the middle of the data. The middle when the data is placed in order, though. So a problem that'll trick somebody is you'll give them 10, 2, 1, 7, 5 is the data set, and it asks what's the median. And somebody's like, okay, I'm going to eliminate the lowest and highest, the next lowest and highest, and oh wow, there's one sitting in the middle, and they think that's the median. And it's totally wrong because you didn't put the data in order first. You should have done 1, 2, 5, 7, 10. It's not just the one sitting in the middle. The median is the middle value so that there's an equal amount of smaller and bigger numbers. 5 is the median because there's two numbers smaller than 5 and there's two numbers bigger than 5. It's not just because one's sitting in the middle. If you have an odd amount of numbers like 5 or 11 or 7, then there'll be exactly one number in the middle, and once you put them in order, that's the median. If you have an even amount of numbers, then you have to average the two that are in the middle by adding them up and dividing by 2. So that the median always comes down to 1 or the other case. You either have 1 exactly in the middle or you average 2 that are in the middle. The mode is the most frequent occurrence. Which one happens the most? Now, take this for example. What if you have 1, 2, 3, 4? Then we say there's no mode or none. If every number occurs equally, then there's no mode. If every number happens once, if every number happens twice, or 3 times, or 4 times, there's technically no mode. You have to have at least some numbers that happen more than others to have a mode. So if you have 1, 1, 2, 3, 4, now the mode is only 1, because that's the one that happens twice. But you could have 1, 1, 2, 2, 3, 4. There can be a tie. There can be a 1 and a 2 for the mode. There can be multiple modes. The only thing that can happen is, say every number happened twice. Say you had 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, 2 6s, then you're back to no mode. At least one number has to be larger or smaller than others if there's ties to have multiple modes. Or what if you have 1 1 1, 2 2, 3 4? There's a misconception among students. They think any number that repeats is a mode, and that's not necessarily true. Here's one where the 1s happen 3 times and the 2s only happen twice, so we're back to 1 being the only mode. But if there were 3 1s, 3 2s, a 3 and a 4, then you would say 1 and 2 again. So most of these things are very easy to do, which is why they teach them as low as junior high. Any junior high kid could catch up on this and understand these 3 concepts. But we use them a lot in real life and in statistics, so that's why we're covering this again. Another one they use in statistics you may not have heard of back in junior high is called mid-range. Mid-range is an average of the lowest and highest. So take the lowest number called the minimum plus the maximum. Lowest plus highest, or highest plus lowest, order doesn't matter when you're adding. Lowest plus highest or highest plus lowest, and divide by 2. So it's kind of a rough average of the center. The problem with this, all 4 of these, is sometimes one extreme value can greatly change the answers. If I have 1 1 1 2 2 3 4, but I change that to 1 1 1 2 2 3 and 40. When one number is greatly larger or smaller than the rest, that's called an outlier in statistics. And later in this chapter, there's a calculation you can do that will definitively say yes or no if something's an outlier. At this point, all we do is just estimate that, yeah, that seems like it's greatly larger than all the other numbers. An outlier can greatly affect 3 of these 4 calculations. If you add up 1 1 1 2 2 3 4, that's only 7 8 9 10 11 14. And there's 3 4 5 6 7 numbers. So the mean is 14 divided by 7. The mean is 2 when I had it as a 4. But if I change the 4 to a 40, the mean goes from 2 to like 7. It almost triples. It more than triples just by changing one number. So if you had an average of 20 on a test versus an average of 70, that's a significant difference if it's 3 or 3.5 times bigger. Also, clearly the mid-range. The mid-range is greatly affected by outliers because it only uses the lowest and highest numbers. So if there's any outliers, that's where they are. Outliers are the extreme low and the extreme high. So if you have any outliers, the mid-range is going to be affected the most by far. And even the mode can be affected either by outliers or just unusual things going on, because the mode is just whatever one happens the most, and literally any number in the data set could be the most. So it could be really low, really high, somewhere in the middle. So all of these measures are pretty good most of the time, and in fact, in many problems, they'll make you calculate all 4 of these in the same problem. And often all the answers are close. In some examples, all 4 answers are identical. So usually all 4 of these answers are either equal or close to equal to each other. But if there's outliers lurking or something weird going on, then the mean, the mode, and the mid-range get greatly affected by that. The one that doesn't care about outliers is the median, because it's measuring the middle of the data. Outliers never happen in the middle. They're at the beginning and the end. So go back to my one example of 1, 2, 5, 7, and 10. The median is 5 because there's two numbers smaller and two numbers bigger. You could change the 10 to 100 or 1,000 or 1,000,000, and all the other answers get greatly changed, but the median's still 5. It doesn't care what's happening way at the beginning or way at the end. So they call this resistant to outliers. The median is resistant to outliers. It doesn't care if there's outliers. Its answer does not change if you change the highest or lowest number to anything. So the blank is resistant because it is not affected by extreme values. So that's the median. If you ever go with a real estate agent to buy a house one day, they'll take you to a neighborhood and say the median house price in this neighborhood. The real estate agents are smart and they do median over mean. Everybody else uses mean for the most part in real life. But in a neighborhood, there could be one house that's really like run down and doesn't cost that much, or maybe there's like a mansion. There's always like the best house in the whole neighborhood. So any one house can greatly affect the average price if there's one house really high or really low compared to the others. So they do a very good job about using the median home price because median isn't affected by one value like that. Okay, here it is. I got a data set, 1, 2, 3, 4, 5, 6 numbers. So first thing you should do is put them in order because the median has to be in order. And the mode, it helps to have them in order. And same with the mid-range. It turns out the mean doesn't matter if they're in order or not. But the smallest number here is 31, then 63. So even though you don't need them in order for every single answer, if you're going to do all 4 answers, it's just helpful to put them in order first. There's 2 different 75s, and we do want to include repeats. If this is like test scores in a class, 2 students could get a 75 on the test. 89 and 98. So maybe this is 6 students. I took a sample of 6 students from a class and found their test average. What is the mean, median, mode, and mid-range for these 6 students? The mean is when you add them up and divide by how many there are. So still, we don't need a real fancy calculator to do this. I'm just going to use a plain, simple calculator right here. So if I do 31 plus 63 plus 75 plus 75 plus 89 plus 98, and then that's the sum, 431. There's 6 numbers here, so I divide by 6. 71.8. Okay, median. Put this answer in, 71.8. This is a case where they don't want you to check the answer yet. You have to answer all 3 before they let you check it. What I do for the median is put them in order first and then eliminate the lowest and highest, eliminate the next lowest and highest, and keep going inward until there's either 1 or 2 numbers in the middle. Here there's 2 numbers in the middle, so then you'd have to average those 2, although the average of the same number twice is itself. If you get a 90 on your first test and a 90 on your second test, your test average will literally be 90 because the average of 90 and 90 is 90. So the average of 75 and 75 is 75. And then the mode is 75 also because 75 is the only number that repeats. If there's only 1 repeat, that's definitely the mode. And see what I said about earlier, how sometimes all these answers are the same. Now 2 of these were the same, but the other one's pretty close. And they're not asking for the mid-range now, but I know they asked for it later, so let me just do one of those. Mid-range, you would take the lowest number, 31, plus the highest number, 98, and you average them, divide by 2. It's the same thing you do for the median when there's 2 numbers in the middle. So 31 plus 98, and then divide by 2 is 64.5. So sometimes when you calculate all 4 of these, you get like a 20 and a 100 and a 50 and a 70, and they're like all totally different from each other. Here they're all pretty close. 2 of them are identical, and they're all within 10 units of each other too. So both the median and the mode were 75. So you can say there is no mode or there's at least one mode, and then this says mode or modes, plural, because they don't want to give away how many there might be. And that is also 75. So now all those are correct, and I got the green check at the top. Okay, same question. You can have negative values, so this is the same thing. They want me to do mean and median first, just to show you that if they only ask for the mean, you don't have to have them in order. I can do 24 plus, in this calculator, if you type 22 and then hit this plus or minus button at the bottom, that makes it negative 22. So I'm doing 24 plus negative 22 plus 20 plus 9 plus 24. And there are 1, 2, 3, 4, 5 numbers, so divide by 5, and the mean is exactly 11. There's only 5 numbers here, so you can put these in order, but I can probably do this quickly just by the way it is. Eliminate the lowest number, 9, and one of the two highest numbers, 24. Now, oh, actually, the lowest number is 22, negative 22, sorry. The lowest number is negative 22, and the highest number is 24. Eliminate those two. And now eliminate the next lowest, 9, and the next highest, 24. There's exactly one number in the middle, and it happens to actually be in the middle right now, too, but that's just a coincidence. So the median is 20, because if you put them in order, there would be a 20 in the middle. There would be two numbers smaller than 20, 9 and negative 22, and there's two numbers bigger than 20, both of the 24s. If the data set's small enough, maybe you can tell which one's in the middle without actually sorting them. There is a mode because 24 happened twice, so again, one mode of 24, but sometimes we say no mode. So they did one example where there were 6 numbers at the beginning, and then another one where there's just 5 numbers. I mean, just to show you, it can make a difference when you're doing the median if there's 5 or 6 numbers. Okay, another type of way to find mean, median, mode is with these frequency distributions. And the issue here is we're going to be estimating these answers because there's no way to know them exactly. There's 4 people who have an answer from 0 to 13, whatever this data is about. Maybe these are people's ages. Maybe I'm at a movie theater and there's 4 people in there aged 0 through 13. There's 14 people aged 14 to 27. There's 7 people 28 to 41, and so on. Well, I can't know out of these 14 young people what ages they are. All I know is they're somewhere between 0 and 13, but they could all be 13, they could all be 5, they could be 5 different ages. So there's no way to know. So the way you handle this is you find the midpoint of each class. Remember, we did that in chapter 2. If you find the midpoint of each class, the first class is 0 through 13. The midpoint is the same thing as the median when there's 2 numbers in the middle. If you average them, this is like the mid-range too, add them up and divide by 2, that's the midpoint. And there's 4 people that are aged 0 through 13, so all I can do, the best I can do is assume they're all in the middle. If they're all about 6.5, that will be the closest estimate to what the real average is. And the real average could change a little bit if I change these 4 people, if they're all really young, like 1 and 2 year olds, or if I change them to teenagers, 12 and 13, then the actual average could change even with a similar group of people. But because there's literally no way to know which ones they are in that range, the best we can do is just use the midpoint. 14 through 27. So if you do 14 plus 27 and divide by 2, that's the midpoint of that frequency of that class, 20.5. Now, one thing that'll happen is you'll start to see a pattern in the answers. So there's 14 of those. So the next class goes from 28 to 41. 28 plus 41 divided by 2 is 34.5. That was the 28 through 41, and there's 7 of them. You see here how it's going up 14, and that's because this is going up 14, and this is going up 14, up 14, up 14. So the midpoints will continue to go up by 14, and then you can stop averaging them if you realize that, and just keep adding 14. So the interval from 42 to 55 that's got a 10, halfway between 42 and 55 is literally 48.5. And halfway between 59, 56 and 69, apparently halfway between that is 62.5, and there was a 13 frequency there. So once you get the midpoints, then you add up, or you find all the products next. So take each midpoint and multiply by the frequency. Because if there were 4 people age 6.5, if you had 4 people age 6.5, you would do 6.5 plus 6.5 plus 6.5 plus 6.5 if you were like adding every single person. 24.5 just for those people. But the shortcut is to do 6.5 times 4, then you don't have to add it up 4 times. 6.5 times 4, something's wrong because I didn't get the same answer. Oh, see, I didn't type this one right. See how, oh, you can't even see it, but there's, I typed that other one wrong. It was 6.5 plus 6.5 plus 6.5 plus 6.5. It's actually 26, not 24.5. So this is 26. Now do this 20.5 times this 14. And you wouldn't want to have to add that 14 times. 287. Now do 34.5 times 7. 241.5. Anything times 10 is easy. It just moves the decimal place over, so that's 485. And then 62.5 times 13. 812.5. So now add all 5 of these. The 812.5 plus 485 plus 241.5. I'm adding them from bottom to top, but adding order doesn't matter, so as long as you do them all. The total of the products is 1,852. If I knew every person's actual age and added them all up, it would be somewhere close to this, actually. It wouldn't maybe equal it exactly because I'm estimating each one. Then if you add up the frequencies, that's how many people there are. So this is how we're kind of doing the average in chunks rather than individually. If we add 4 people in that age group, and then 14, and then 7, and then 10, and then 13, there's 48 people in this sample. If I knew all 48 people's actual average and added them up and divided by 48, that's how I would get the real average. So this is the only, this is called a, this is for grouped data. When the data is grouped together, there's no way to get the real average, but this will always be pretty close to it. This is a grouped average. And it would be 1852 divided by 48. 1852 divided by 48. And then usually when it's a long decimal, they'll tell you to round it somewhere. Round to 1 decimal place, it says 38.5, but after the 5 there's an 8, so add 1 to the 5 and make it 38.6. So you can do grouped averages if you treat every class and work with the midpoint of each class and just assume everybody's in the middle, because some people will be above the middle, some will be below. In the long run, it'll kind of average out. Okay, so what if I have a stem leaf plot? Remember that from chapter 2, stem leaf plot. These are the 0s, the 10s, the 20s, and the 30s. The great thing about a stem leaf plot is you actually can know every individual one. In those frequency distributions, I can't tell what ages people actually are. But now I can know everybody's answer. The first person is 6. The second person is this 1, 0, which is 10. The third one is the 1, 7, which is 17. Then there's 4 people in the 20s. There's a 27. another 27, a 28, and a 29. And the highest one was 37. So I literally just added every person's answer up. And there are 1, 2, 3, 4, 5, 6, 7, 8 people in this sample, so divide by 8. And this is not just an approximation of the mean, this is exactly what the mean would be if I wrote every initial answer down, added them all up and divided by how many there are, 22.6. And notice the next digit is a 2, so you don't add 1 to the 6, leave it 22.6. Round to 1 decimal place. And I can't check it yet because they want me to do the other ones. So there's one number that repeats. There's two 27s. Everything else happens once. So there is one mode. That's weird. We keep getting exactly one mode every time, but 27's the mode. And then the median, if you eliminate the lowest number 6 and eliminate the highest number 37, now eliminate the next lowest number 10 and the next biggest number 29. Then eliminate the next lowest number 17 and the next highest number 28. It turns out there's 2 numbers left in the middle. We have 8 total numbers, so eliminate the 3 lowest and the 3 highest. That's 6 of them. There's 2 left in the middle, and they both happen to be a 27. So the average of 27 and 27 is 27, but if you forget that rule and add them up and divide by 2, voila, 27. And here's another example where the median and the mode are exactly the same. That's usually not true, and that's kind of weird that they keep making that happen. But again, here all 3 answers are pretty close together. Okay, the National Center for Health Statistics reported in a recent year that the mean height for U.S. women aged 20 to 29 was 63.2 inches, and the median was 63.3. If a histogram were constructed for the heights of all women in this age group, what would you expect it to be? Skewed right, skewed left, or symmetric? So here's something you probably didn't know. If the mean and median turn out to be equal to each other, which can happen, if the mean and the median are equal to each other, then they're both right smack dab in the middle in a histogram. And the histogram will be symmetrical, or at least approximately symmetrical. So if you make a histogram that's symmetrical, the mean and the median are literally both smack dab right down the middle when they're equal. Well, this problem, they're clearly not equal because they said one was 63. Well, they're really close actually though. 63 I thought it was 62 something, but 63.2 and 63.3. They're so close, almost identical, that this is approximately symmetric. Definitely approximately symmetric. If I tried another one, let's see if I can get one where they're different. Yeah, see here, they're a lot different this time. Now one averages 400 and the other one is 250. They're greatly different from each other. So whenever they're different, then the median, remember the median is the middle value. So you always put the median in the middle of a histogram. The median's always in the middle no matter what. The mean will go, if the mean is bigger than the median, the graph will go longer that way. So if the mean is bigger than the median, like this one where the mean is 400 and the median's only 250, the mean will go towards that side that's bigger because it is bigger. So this is one where you'll end up getting like a longer tail to the right. There'll be more bars, significantly more bars to the right than the left when the mean is higher. So that's skewed right when that occurs. Unless, let me think for a second, the mean's definitely to the right, but I'm not sure about the bars actually. Now I'm doubting myself on that because there should be an equal amount of values above and below the median. No, yeah, it would have to be like this, skewed right. So this would be skewed right. Yep. And then, so the opposite case would be obvious if it's longer the other way. The median's always in the middle. And if it's longer to the left, significantly longer to the left, Here I got one where I've got 4 to the left and only 2 to the right. The mean's going to go where the more are, or not where the more are, but it's going to go towards the side that's longer. So if the median was, say, 300 and the mean was 200, you definitely know which way the mean's going. The mean, if the mean's smaller than the median, it's on its left. If it's greater than the median, it's on its right. And wherever the mean is going, that's what I wasn't sure about. Wherever the mean is going, there'll be more bars that way. And that's why it's skewed that way. This is skewed to the left. So in problems like number 6, they'll tell you the mean first and the median second. If they're roughly equal, you definitely say symmetrical. And if the mean is bigger than the median, it's skewed right. If it's smaller, then it's skewed left. A company examines the audit records of 93 bills. They find that 10 of them had no errors, 8 had 1, 14 had 2, and 61 had 3. This is what's called grouped data, not grouped, this is called weighted. This is a weighted average. So we had number of errors. You could have 0, 1, 2, or 3 errors in your records. 0, 1, 2, or 3, and then here's the amounts of errors. How many times these occurred. Maybe I should call this frequency, actually. The frequency of times that these number of errors occurred. So there were 10 times that they made no errors in the records. There were 8 times that there was 1 error. 14 and 61 for the other 2. So this is done similarly to the group data. You always do a product column when you have these 2 columns going on. Make a product column and just multiply straight across, which 3 of those are pretty easy. 0 times anything is 0. 1 times anything is the anything. And 2 times 14 is simply 28. Even 3 times 61 isn't hard because you do 3 times 1 and you get 3, and then you do 3 times 6 and you get 18. So I did all 4 of those without even a calculator. You always add the products first, even in that other kind with the group data. So group data or weighted averages, you always find the products and add the products, no matter what. That's always the first 2 steps. 219. And then there's 2 steps to go. You add one of the other 2 columns, and in the group data, it's obvious which one to add because you're not going to add the ones that have dashes in them. 0 through 13 and 14 through 27, how are you going to add that up? So that was obvious which one you're adding. You usually add the frequency, which is how many people there are. So 10 plus 8 is 18. 18 plus 14 plus 61. There are 93 people here. In fact, I remember the problem even said that there were 93 records looked at. So you always add up one of the other 2 columns, and usually it's the one about the number of people. So this is called a weighted average. Whoops, weighted because some categories weigh more than others based on how many times they happen. There's a lot more times they're making 3 errors than 1 error. So that one's going to weigh more into the average. And if you do 219 divided by 93, that would be similar to having 93 answers, adding them all up, and they add up to 219 and dividing by 93. You're still kind of doing an average where you add them all up and divide by how many there are. You're just getting the sum a lot more easily than literally adding 93 things together. So, whoops, I put plus. 219 divided by 93 is, and then we probably nearest 10th, but let me double check. You got to be careful because they'll sometimes change what they want you to round to. It doesn't even say here. Find the mean number of errors. Okay, so 2.35. Maybe they'll take different amounts of decimals. 2.35. It doesn't say where to round. So notice that that's pretty high in the list. The middle of the list is 1.5. But the answer was almost 2.4. The answer went away from the middle this way because there's so many down here on the 3. The 3 weighs a lot more, so it's pulling the average that way. That's why it's called a weighted average. And then the median is the middle of the data. So if you take 93, which is an odd number, if you subtract 1 because I want to leave 1 in the middle, there's 92 other numbers besides the one in the middle. So if you divide by 2, 46, there'll be 46 small numbers, then the one in the middle, and then 46 big ones. So if I could either eliminate the 46 lowest numbers or the 46 highest numbers, that would be the one in the middle. And because there's 61 threes, and there's only 32 that are less than 3, the first 32 numbers will all be less than 3, and I still need to go 14 more numbers till I hit the middle one. So, and there's 61 threes, so you could write 46 threes down and still have some left over. So there's even some threes here. And then there's only 32 of them that are 0 through 2. So the first 32 are 0 through 2. And then there's still 14 more threes. Then you got the 3 in the middle, and then there's 46 more threes. So clearly the median is 3, and they did this on purpose. That's why they made the 3 so high, because otherwise it might be hard to tell. But the median will turn out to be 3 because there's so many threes, it'll still be in the middle. There's enough threes to have more than half the data be a 3. Okay, here's where they introduce mid-range. I taught you this already. The mid-range is largest plus smallest, or smallest plus largest, because adding order doesn't matter, divided by 2. The mid-range is not resistant because it's greatly affected by outliers. It's not resistant. The only one that is resistant is the median. The mid-range is not resistant to outliers. Literally, if there's any outliers at all, you're going to hit them instantly on the mid-range. The mid-range is affected by extreme values because it only works with the extreme values. Now, if a data set doesn't have any outliers, if you just have 1, 2, 3, 4, 5, then the mid-range is a good measure. But anytime there's outliers, they always happen at the largest and smallest values, so then this can be greatly affected by that. Okay, if all the data set are the same, okay, wait, we need to stop for a second. Okay, so we just did problems 1 through 8. Problems 1 through 8 were the section 3.1, and I can tell we've switched to 3.2 now. Problems 9 through 15 are 3.2. Okay, so we're kind of a little past the halfway point. I'm going to give you the magic word of this video, and you might remember the theme of the first 3, so I'll pick another one in the same theme. Let's go with the 4th magic word. Email this to me. The 4th magic word is Galveston. Galveston is the 4th magic word. And hopefully you keep watching the rest of the video now, though, because 3.2 is similar to 3.1, but from a different point of view. In fact, before I write this down, let me show you this again. In 3.1, you do the center, the central tendency. And there's 4 common ways to do that: mean, median, mode, and mid-range. Mid-range is kind of an outlier type. It doesn't happen all that often. So by far, the 3 most common measures of average or center are mean, median, and mode. In 3.2, this is called the variability or the spread. How does data spread out? You can be very narrowly spread or very widely spread and still have the same average both times. So a spread of data is a different concept than the center or the average. And there's 3 main ways to measure this. One's called range, which is an extremely easy thing to do. You just take the maximum value minus the minimum, the highest minus the lowest. If you have a data set that goes 1, 2, 3, 4, 5, then the range is 5 minus 1, which equals 4. Then this is how I knew we were in section 3.2. This question's asking for variance. Variance is a 5-step process. It's not, any one step is not hard, but you just got to remember the 5 steps. And then standard deviation is basically the 6th step of the process, but it's always the square root of the variance. So it's very easy to do. If you get the variance right, it's very easy to get the standard deviation. You just literally square root your answer to get that one. Now, before we work one of these, I know what they're getting at in this problem. So let me show you an example. Say we have 1, 2, 3, 4, 5. It turns out if data is symmetrical or evenly spread out, then the mean, the median, the mode, or at least the mean and the median are the same. Here, the mean and the median are 3. Clearly, the median's 3. It's the one in the middle with the data in order. And if you add 1 plus 2 plus 3 plus 4 plus 5 and divide by 5, it'll equal 3. So if data is evenly spread out like this, the mean and the median are the same. So what if I add 20 to every number? Did they mention something? No, it just says they're all the same. Okay. So let's say you add 20 to every number, or let's just add 10 to every number. 11, 12, 13, 14, and 15. Now both the mean and the median are 13. I add 10 to every number, one by one. And it's probably not surprising that the mean and the median went up by 10. That's always true. If you add the same amount to every number, the mean and the median will go up by exactly that amount. But notice the data hasn't spread out any differently. The middle is 3. I got one number below that and one number above and 2 below and 2 above. That's the spread of the data. The exact same thing is happening here. This is 1 below, this is 1 above, this is 2 below, and this is 2 above. So when you learn how to calculate variance and standard deviation, it'll be strange, but if you add the same amount to every number, they stay the same. So actually, I just saw this problem, and this is not what it's actually asking for, but they might ask that later. This says if all the data values are the same, what would happen to the sample variance? So say every number was the same. Say that you had 7, 7, 7, 7, and 7. Well, how far are they spread out from the middle? That's what the variance is about, is how far do numbers away from the middle spread out from the middle? Well, this is 0 away from the middle. This is 0 away. This is 0 away. This is 0 away. If all data are the same, which is very rare in collecting data, it's very rare if you collect data that every number would be exactly the same. But if every number is the same, then both the variance and the standard deviation will equal 0. And at this point, you kind of have to take my word for it because you haven't learned how to actually calculate these. But you'll see in the process of calculating them, I'll come back to this and show you why this is true when we do a problem where we're actually calculating it. But it is true that if every number is the same, then they're not spread out from each other. If you're not spread out, you have a spread of 0, basically. And that's really the only time it should be 0. Okay, so they want me to calculate this now, and I have 2, 4, 6 numbers. There's 6 original numbers given to me. This is number 10, I believe. Yes, number 10. So it turns out it doesn't matter if the data's in order. 16 and 30. 22 and 18. 11 and 10. Now, they're not asking for the range in this problem, but I'm just going to tell it to you anyway because I know it comes up later. Range is max minus min. It's its own separate answer. It's kind of like when you find the mean. When you find the mean, that has no effect on the median answer or the mode answer. They're just separate answers. This is just a separate answer. The highest number here is 30. The lowest number is 10, so if they were to ask for the range, it's 20. Usually they ask for range, variance, and standard deviation in a given problem like this, but they're only asking for the variance and the standard deviation. So it's a little weird in my opinion they didn't also ask for the range, but that's okay. So here comes the variance next. This is a 5-step process. Luckily, every step's mathematically pretty easy, especially if you have a calculator. Step 1, you find the mean. That's easy. We've been doing that since junior high. Take the original numbers, 16 plus 30 plus 22 plus 18 plus 11 plus 10, And since there's 6 of these, you divide by 6. Now, unfortunately, if this doesn't come out exactly, oh, dang. If it doesn't come out exactly, then this gets really messy, unfortunately, because you don't want to round too soon. So 17.8333, I'm going to put at least 4 decimals here. 17.8333. And then step 2, you do each given number, which I'm just going to call x because I don't know in a data set that if I do another problem, x just represents any number that could come up. So you take each number that's given to you and subtract the mean. And this is where it can get messy with decimals. So I'm literally doing, the first number is 16, and I'm trying to subtract 17.8333. So one thing that could help is many calculators have a way to store this in memory. I'm going to store this in memory. Memory store. Store this in memory. And then I can do 16 minus memory recall. And if only the mean was 17, I wouldn't have to deal with all this, but unfortunately they gave us a bad example. See how it's a big messy decimal, but I'll just round this to 4 decimals now. Negative 1.8333. Now, step 3 is related to step 2, and you can finish all the step 2s before you even do step 3, but then the problem is, especially with these messy decimals, you're going to have to retype answers you already had on your calculator screen to do the next step. So this will be helpful right now since I have one of the cases where the decimals are messy. Is step 3, you take the step 2 answer. That's what's one nice thing about this is there's 5 steps to know. But every step you take a previous answer and do something to it. So I'm going to take step 2 and square all the answers. And it's really nice while this answer is still on my calculator screen, I have a squared button right here. If I hit squared, I don't have to retype negative 1.833333 and then hit squared. If you do all the subtractions first and then do the step 3 second, then you got to retype them and square and hope that you have enough decimal places that it won't be a rounding issue. So I'm going to make 3.3611 here. 3.3611. So that was 16. Now go to 30. 30 minus this 17 number. So 30 minus memory recall. This is what helps me is I can just type that whole, I don't even have to type it. I just call it up and it's all there and there's no rounding issue. 12.1666 repeating. But rather than writing it down and coming back later and retyping it, if I hit the squared button right now, it'll square it instantly for me. 148.02777. 148.02 777, so I'll make that 78. The next digit is 22 minus our 17 number. 22 minus memory recall is 4.1666. I'll make that 667, and now square it. 17.3611. Next number is 18. See, this can get annoying if you have to do a lot of these. 18 minus 17.8333. 18 minus memory recall. 17.833 equals 0.1666. Square it. 0.0278. 2 more to go. 11 minus 17.833. 11 minus memory recall equals negative 6.8333. And then Square it. 46.6944. Oops. 46.6944. And finally 10. 10 minus 17.8333, which should be negative 7.833. It's the same as the previous answer, except one farther away. But you can do it in here. 10 minus memory recall. See, negative 7.8333. Square it. 61.3611. 61.3611. Okay, the first person who came up with this calculation about 100 years ago, this was their thought. They were trying to create a situation where I want to know how far away from the middle every number is. Some numbers are above average, some numbers are below average. Notice in my list of answers in the second column, 3 of them are negative and 3 of them are positive. That doesn't always, sometimes it's 4 and 2, but see how the biggest number is a positive 12, and the negatives don't have a negative 12. They have a negative 7 and a negative 6. So, but what ends up happening is if you add all the positives and add all the negatives separately, they equal the exact same thing. 12 point whatever plus 4 point whatever plus 0.1, whatever that'll add up to 16 point something. If you add the negatives, they'll add up to negative 16 point something too. And that always happens. If you add up the lists too, it always adds to 0. And this is why they had the previous problem. The variance and the standard deviation should only have an answer as 0 if every number is the same, because then the numbers are not spread out from each other. Clearly, these numbers are spread out from each other. They're not all the same. So it doesn't make sense that the answer would be 0. But it's just the nature of what the mean is about. The mean is a value, a balancing value in the middle of the data, not exactly in the middle like the median, but it's somewhere near the middle so that there's an equal amount of positive and negative distances away from the mean. So the person who invented this statistic had to come up with a way to make the negatives go away. And one way in math to make negatives go away is to square things. Anything squared is positive. Another option could have been absolute value, but they just chose squaring. Although the downside to squaring is you make them a lot bigger. The 12 went all the way up to 148. That's way bigger. It went from a double digit to a triple digit. Even the single digit 4 went to a double digit of 17. So squaring, unfortunately, makes them too big, but that's the only way that's one of 2 ways to make them positive. So step 4 is you want to add up the step 3 numbers. Sum up the step 3s. Because if you sum up step 2, it'll always be 0, so that clearly wouldn't make sense to do that. So let me see if I can put this where we can see it all. 3.3611, I'm adding these 6 numbers right here, plus 148.0278, plus 17.3611, plus 0.0278, plus 46.69, I think that's a 4, can't even read my own writing now. 4.4, I think it was, and then 61.3611. And I am rounding these, so there's a slight issue that maybe this rounding will cause an issue in the end, but that's the best we can do with messy decimals. So 276.8333, 276.8333. Just put a bar here because I can't write it all down. So the final step for variance is to divide, and it can depend if you want population variance or standard or sample variance. See how they say sample variance and sample standard deviation? That's much more common than population. Usually we don't know the whole population, so we would have to deal with a sample. If you want sample variance, you take this sum right here, and you divide by, remember how we got the mean? The mean was the sum divided by 6. That's how I got this 17 number, because there was literally 6 numbers in the original problem. The size of the sample is called n in statistics. I have a n of 6 here because there's a sample of 6. And that's what you divide means by. The means are add them up and divide by how many there are. Strangely, on variance, you divide by n minus 1 if you're doing sample variance. If you do population, then they still divide by 6. But so to get the first answer, I need to take this 276 number and divide not by 6, but by 5, 1 less than the sample size. Divide by 5. This is the answer to variance. It took me 5 steps to get it. 55.36666, or maybe 0.4. 55.4 maybe. Oh, they want 2 decimals. Okay. 55.37. So that can be hard to get that answer because you have to remember all 5 steps, and sometimes there's messy decimals like this. And then once you get the variance, though, the last answer is easy. In essence, the standard deviation is the 6th step of the process. And you just square root the variance. Literally, you square root the answer you just got. So standard deviation is easy. Square root this 55 number, and it's 7.44. Now, let me do this one more time with much nicer numbers because I don't know how messy it'll get. Maybe they'll make you do this again with easier numbers. Say it was 1, 2, 5, 10, and 20. Well, actually make sure it comes out nice. 15, 16, 17, 18. Let's do 22. Say you only had 5 numbers, so n is 5. And you want to do the variance, sample variance. Sample variance. So first step is to find the mean. Sum up the numbers and divide by n. 1 plus 2 plus 5 plus 10 plus 22 is 40. I did that on purpose to make it come out nice. And there's 5 numbers here, so you divide by 5. That's 8. If the mean is an integer, this isn't as messy as they just made that last example. So step 2, take each number and minus the mean. And if these come out nicely, you don't have to do step 2 and step 3 at the same time if you don't want to. 1 minus 8. 1 minus 8 is negative 7. 2 minus 8 is negative 6. 5 minus 8 is negative 3. 10 minus 8 is 2. And finally, 22 minus 8 is 14. See, that was easy. I didn't even need a calculator to do that. But notice the 2 positive numbers are 2 and 14. That adds up to 16. The 3 negative numbers are negative 7, negative 6, and negative 3, while 7 and 3 is 10, plus 6 is 16. The negatives add up to negative 16. The positives add up to positive 16. That always happens. That column will add to 0 every single time. In fact, you should probably do that yourself to double check, because if it doesn't add to 0, you made a mistake. So then, if I square them all, then they'll turn positive, and then they won't add up to 0. That's the only reason we have step 3. But negative 7 squared is going to take a single digit number and make it double digit all the way to 49. Negative 6 squared is 36. Negative 3 squared is 9. 2 squared is 4. And 14 squared is 196. And maybe you didn't know that one off the top of your head, but that's one that I know. So then step 4 is to sum up the third list, the third step, because that one won't add up to 0. That's why we square them all so they won't be negative. If they're all positive, there's no way it can add up to 0. 49 plus 36 plus 9 plus 4 plus 196. The sum is 294 this time. And then if I want sample variance, not population variance, then you take your 294 and you divide by 1 less than how many numbers there were. We divided the mean by 5, so we're going to divide the variance by 4. It's always one less than what you divided the mean by if you're doing sample variance. 73.5. Now, as I said on the other problem, the standard deviation is technically the 6th step of the process, but the variance, they usually ask for this answer, so that answer is done. The only reason standard deviation exists is because of the way squaring numbers make them bigger. So by squaring them, you're trying to make them positive, but you also make them bigger. The 14 went all the way to almost 200. The opposite of a square is a square root. That's why we square root the variance to get the standard deviation. If you square root this 73 number, it drops down to 8.57. This represents the spread of the data better than the variance does because the variance has been inflated. What it represents is the positive version of these numbers. If you had 7, 6, 3, 2, and 14, this is sort of it's not exactly the average, but it's sort of the average of those numbers. The sort of average of 7, 6, 3, 2, and 14 is 8.57. 8.57 is pretty close to all those numbers if you think of them positively. 7, 6, 3, 2, and 14. All 5 of those are fairly close to 8.5. 73, none of them are even anywhere near 73. So the variance is just too large because you square numbers to make them positive, but you inflate them by doing that. So that's why we have standard deviation. Standard deviation brings it back to the level it should be at. And I did my example in about 1/10 of the time it took me to do this messy one. And I did most of it without a calculator too. So if they give you a nice problem to do in the test, then, and unfortunately when you have 6, that's an issue. 1, 2, 3, 1, 2, yeah, 6 is bad because when you divide by 6, it often doesn't come out exactly. So I'm just going to add this up and hope it divides evenly. They got 2 examples here, but it's another messy one. So I'm not going to go through this a second time. It's the same as the other problem I did. But maybe if you do one where they have 5 numbers, that would be better, or 10 would be better. But yeah, unfortunately, they have 6 on both of those. And I don't know if I get this one wrong on purpose and try another. Is it always going to give me 6 numbers to start with, unfortunately? See, try another. No, see, here I got one with 5. See, that's better. So if that happens to you in the homework, just get it wrong on purpose. Now it'll be easier to do. Now we can do it because it won't take so long. 18 plus 5 plus 19 plus 12 plus 25. And then you divide by 5, and even though there will be a decimal here, when you divide by 5, it's not a messy decimal. It's just 15.8. Okay, so I'm going to redo number 12, but with easier numbers to work with. 18, 5, and 19. 12 and 25. And this time the mean was 7.8. Oh, sorry, 15.8. That's better than 0.83333 repeating. So if it's, at least if it stops, then it's okay. So step 1, find the mean. Step 2, do each given number minus the mean. And even though there is a small decimal here, I would go ahead and do step 2 and step 3 at the same time. It'll be less typing if you do that. So take the first number, 18. 18 minus 15.8. 18 minus 15.8, 2.2. And then immediately square that number. Squared. 4.84, and see it's not a messy decimal at least. So if you're working with dividing by 5, then things don't get crazy. Now do 5. 5 minus 15.8. This will be some negative answer. 5 minus 15.8 is negative 10.8. Now immediately square it, and it'll be positive. And see, this is the advantage. By hitting squared right now, I don't have to come back later and type negative 10.8 before squaring it, which just takes more time. And actually, if you type negative 10.8 and hit the squared button, some calculators try to claim it's negative because you're not squaring the negative by doing that. So watch out. If you get any negatives in your third column, something's wrong because it should never be negative here. 116.64. Now do 19 minus 15.8. 3.2. And square it. 10.24. 2 more to go. 12 minus 15.8. 12 minus 15.8 is negative 3.8. Negative 3.8 squared. 14.44. And finally, 25. 25 minus 15.8 is 9.2. 9.2 squared is 84.64. When we got the mean, I added them up and I divided by 5 because n was 5. So when I do step 4 now, the variance equals the sum of the squared numbers, and I'll type them from bottom up since I already have the 84.64 on my screen, plus 14.44, plus 10.24, plus 116.64, and plus 4.84. The squared column adds up to 230.8. Divided by 4, not divided by 5, because it's always one less when you're doing sample variance. So it came out to exactly 57.7. The sample variance is 57.7 exactly. And then this is easy, square root that to get the sample standard deviation and round to 2 decimal places. 7.59, but there's a 6 after that. So if you're adding 1 to this 9, one way to do that is don't think of it as 9, think of it as 59. Go to the next number before the 9 that's not a 9. Think of it as 59 plus 1. 59 plus 1 is 60, so this will be 7.60. Which technically you don't need the 0, but I'll just emphasize it. Okay, so, I must have made one little error in here somewhere. Okay, so the mean, let me make sure I wrote the numbers down right, was 18 plus 5 plus 19 plus 12 and 25, and definitely divide by 5. 15.8, so I did the mean right. And let me make sure, maybe they said population. That's maybe what I did wrong. Oh, yeah, they did switch to population. Okay, I didn't notice that. So, yeah, the point of this problem is population. Then the one step that's different in population is you do divide by 5. You only divide the same as the mean gets divided by if you're doing population variance. But it's much more common to do sample variance. So 230.8, I should have divided by 5, not 4. So the correct variance is 46.16. And then the square root of that to 2 decimal places is 6.79. Notice there's a 4 after that, so don't add 1 to the 79. 6.79. So that's the only thing I did wrong is I didn't pay attention that they switched to population variance. But that's good because we did sample variance twice. Okay, if a sample variance is 4, then what's the standard deviation? Literally, this is easy. That's the square root. The square root of 4 is 2. So this is an easy problem. And you should remember this rule. It's very nice. Anytime you know the variance, you can just square root and instantly get the standard deviation. It's the 6th step of the process, but it's the easiest step probably. And you can go backwards. If you know the standard deviation is 3, well, then you square it to get back up to the variance. We do this throughout other chapters in the textbook. Sometimes we know variance and we square root to go down to standard deviation, or if we know standard deviation, we can square to go up to the variance. They are related to each other that way. Okay, I know what's happening here. Let's see, what else do we have? Okay, same thing. Yes, okay. So there's one concept left for these last 3 problems. And there's 2 aspects of it. The more important one is called the empirical rule. Oops. Empirical rule. To use the empirical rule, you must have a bell-shaped or symmetrical graph. And at this point, they'd have to tell you that. They'll either say use the empirical rule, or they'll say it's bell-shaped symmetrically. If you had all the raw data and made your own histogram or some other, like a dot plot or a stem leaf plot, if you could tell, oh yeah, this looks bell-shaped, then you could use the empirical rule, but usually they just tell us if it is or not. If it's bell-shaped or symmetrical, then we can use the empirical rule, and we want to use it because it's more accurate. There's another rule to use if you don't know that, or if you're told that it's not that. And the empirical rule, we go to the number of standard deviations. And we just learned how to find standard deviations. So number of standard deviations will be 1, 2, or 3 every time in an empirical rule problem. And then you're supposed to memorize these percentages. If you're within 1 standard deviation in an empirical rule problem, 68% of the time you'll see observations in that range. If you're within 2 standard deviations, it's 95%. And if you're within 3, it's 99.7. Some books call this, most books call this the empirical rule. Some books call this the 68, 95, 99.7 rule, because those are the numbers you're supposed to memorize. One of 2 things will happen. They'll either give you the percentage and ask for the values, or they'll give you the values and ask for the percentage. See how this first problem has the 95% here. It's given me the percentage. And it wants to know what 2 numbers am I between. So once you realize you have a empirical rule problem, and notice it does say bell-shaped right there. That tells me empirical rule for sure. And the 95% is one of the memorized numbers. That's another giveaway. But to do both empirical rule and the other one, you have to know the mean and the standard deviation. They always tell you that in the paragraph. See how there's an average of 32 in the top here, and then it says standard deviation of 4. So the paragraph says an average of 32 and a standard deviation of 4. Make a number line with that. Whenever I'm doing empirical rule, I always make a number line, put the average or the mean in the middle, and it's bell-shaped, so the mean and the median are in the middle. Then add the standard deviation 3 times. If I add 4, add 4, add 4, because the standard deviation was 4. Add 4, add 4, add 4. Then go back to the mean and subtract 4, subtract 4, subtract 4. What these represent are the number of standard deviations away from the mean. The mean is 0 away from itself, but 36 is positive 1 standard deviation above the mean. 40 is positive 2, and 44 is positive 3. 28 is negative 1, 24 is negative 2, and 20 is negative 3. They want to know what scores do 95% fall between. So it says blank and blank. So one key thing is you hope to have between. There are some other cases besides between, but between is the best way to do this if you get a between case. And if they give you one of the three memorized numbers, 95, 95 is the second one. So by knowing that 95 is associated with the second place out, and you're looking for between, then you go to the +2 number and the -2 number. So the answer is this 24 and this 40. Between 24 and 40, 95% of the measurements will land. Between 24 and 40 days, 95% of whatever this is about will happen. Or it can be backwards. Now it says between 28 and 36, what percentage happens between 28 and 36? Well, find those two numbers in your number line. 28 and 36 should be on my number line. 28 is the -1 spot, and 36 is the +1. And they pretty much have to tell you the same number both times. It can't be -1 with +3. We don't know how to do that yet, and that won't happen until chapter 7, actually. So it's really got to be either the 1 and the -1, or the 2 and the -2, or the 3 and the -3, and then literally the answers are 68, 95, or 99.7, whichever one you have. I have the 1 and the -1, so according to the chart, that's 68%. Although you'd have to memorize that for a test, but 68%. And then here's another one. Estimate the percentage between, hopefully it says between, and apparently you can do like above or below, but luckily they're doing the between cases only so far. So between 20 and 44, those probably are both on my number line. Find 20 and 44 on your number line. 20 is the -3 spot, so hopefully the other one's the +3. And it is. 44 is +3. So if I want to be between the -3 and the +3, that happens 99.7% of the time. Okay, almost all. Because 99.7 is almost 100. They could have put 99.7. I've never seen that before, but yeah, almost all. This is a classic case of the empirical rule in this number 13 problem. 14, analysis of daily sales from 600 and 762 local bakeries showed an average of 34.84. So put that in the middle of a number line. The average is 34.84. There's the mean. And I always circle that one to keep track of where it is. And this will be the 0 level. So I'm going to go 3 places to the right, 3 to the left. This will be my +1, +2, and +3 levels. -1, -2, and -3. The average is 34.84, and the standard deviation is 912. Assume that they're bell-shaped, okay? That means empirical rule again. And it's another between. So apparently they're only doing betweens here, which is good. In my HCC classes, they also do like above and below, and those are harder cases, but at least you're only getting the easy cases. The betweens are the easy cases. So the standard deviation is 912. This will be a little more challenging to fill the number line in because it's such large numbers, but 34.84, just use a calculator, plus 912 is 43.96. Plus 912 is 53.08. Whoops. Click it. Plus 912 is 62.20. Now go back to the mean, 34.84, and now subtract 912 3 times. 25.72. Minus 912 is 1660. And minus 912 is 748. The question will say between two numbers, and hopefully both numbers are either at the 1, the 2, or the 3 place. So between 2572, that was the -1 number. Between 2572 and 4396, 4396 is the +1. So I'm between the -1 and the +1. That's 68 on the chart. 68% is when you're 1 away each way. As long as it says between, which all your problems have said between. 68%. Okay, wait. So there's one extra step to this problem. As soon as I noticed there was no percent symbol here, I knew something was off. So 68% is the percentage, but there's a total of 762 local bakeries. So 68% of them will qualify under this question. So this one has an extra step of taking 68%, which is 0.68, and you have to multiply by the 762 total sample size, basically. And the previous problem didn't even mention that third number, so that's why I knew not to do that there. And then it says round to the whole number, so I would round this to 518. Round to the nearest whole number. So 68% is correct, but they're not asking for the percentage. They're asking for how many bakeries. Estimate the number of bakeries, not the percentage of bakeries. So if they don't ask for the percentage, then you just multiply by the total to get that. And notice in the number 13 problem, if I go back to that, every answer here had percentages on the answers when the drop-down menu came down. But this one, there was no percentage in the box. That's why I knew it didn't want a percentage. Okay, what if you don't have a bell-shaped graph? If they don't tell me it's bell-shaped, I can't assume that it is. Or here, the other rule is called Chebyshev's. It was named after a Russian, Chebyshev. So if they say use the empirical rule, or if they say it's bell-shaped, then you use the empirical rule, and you want to use that one because it's more accurate. But if they don't say use the empirical rule, or if they don't say it's bell-shaped, or if they come right out and say it's not bell-shaped, or if they say use Chebyshev's, then we use Chebyshev's instead. Chebyshev's is virtually the same procedure, but it uses different percentages instead. And you only have to memorize the empirical rule one, but I'll add Chebyshev's right here. You only need to know Chebyshev's for the homework. There's a rule where you do 1 minus 1 over k squared, where k is the number of standard deviations. So if I plug in 1 for k, because here's 1 right here, that's k. This is k, this list right here. Well, 1 squared is 1, and 1 divided by 1 is 1, and 1 minus 1 is 0. So Chebyshev says 0% for the first one, which doesn't really tell you a whole lot. So then if you put a 2 right here for the next one, 2 squared is 4, and 1 divided by 4 is 0.25. And then if you do 1 minus 0.25, you get 0.75. So that's why Chebyshev's second value is 75 instead of the 95 that the empirical rule has. So Chebyshev's is just a more conservative rule. All the percentages are lower than the empirical rule. And if you don't know something's bell-shaped or symmetrical, then you can't use the empirical rule. And often the answers are smaller, which is why this procedure works. If you change this to a 3, 3 squared is 9. 1 divided by 9 is 0.1111. And then if you subtract 1 from that, you get 88888 repeating, so it's 0.89 or 89%. So Chebyshev's is 0, 75, and 89 rather than 68, 95, and 99.7. Other than that, you do it the same way. So there's a mean of 49.5, and there's a standard deviation of 3.8. And if k equals 2, then I'm going to use the 75% rather than the 95 that the empirical rule uses. And other than that, you do this the same way. So make a number line, put the mean in the middle, 49.5. Now add that standard deviation 3 times and subtract it 3 times. The standard deviation is 3.8. So 49.5 plus 3.8 is 53.3. That's going to be the positive 1 spot. Add 3.8 again. 57.1 is the positive 2 spot. And add 3.8 again. 60.9. Now go back to the 49.5. Subtract 3.83 times. So first you get 45.7. That's the -1 spot. Minus 3.8. 41.9. This is supposed to be a 4, not a Y. And then minus 3.8 is 38.1. So there's -2 and -3. So this is the same kind of question. They're going to say what percent is between two numbers, or this given percent is what two numbers. It can be either direction for that question. Here it's saying 75% of the periods were between blank and blank. So I just have to know 75 in Chebyshevs. 75 in Chebyshevs is the same as 95 in the empirical world. That tells me to go 2 places each way. So get to +2 and -2 on your number line, and those are the two answers. This 41.9 and the 57.2. 41.9 and 57.2. So it works just like empirical, just the percentages are smaller for each level. Okay, did I miscalculate something? Go back here. It was 53.3 plus 3.8, 57.1. Oh, 57.1. I just wrote it down wrong. Okay, 57.1. Okay, so there it is. And now I got a green check on everything. And this is the end of the 4th video. We've now learned 4 sets of homework assignments. And the 4 homeworks is basically what the test covers. And if you do the review, which is what the 5th video will cover, between doing the 4 different homeworks and the review, plus the 0242 homework helps too with some background knowledge and some just extra practice on the most important types of problems. That's definitely what would make somebody successful on a test if they're able to do all that. So this is the end of video number 4, and send me your magic word.